Space is vast, mysterious, and full of wonders, but it's also home to some of the most terrifying objects known to humanity. From the unstoppable force of black holes to the immense power of quasars, the universe is a chaotic battleground where the laws of physics stretch to their limits. In this video, we'll journey through the cosmos to explore the 5 most terrifying objects that could not only reshape galaxies, but wipe out entire star systems, including our own. Prepare to face the unimaginable as we dive deep into the darkness of black holes, neutron stars, pulsars, magnetars, and quasars. These are some of the most terrifying objects in the universe, and they are far more dangerous than you could ever imagine. Black holes may be the most mysterious objects in the universe, invisible, yet capable of shaping entire galaxies and warping the very fabric of space and time. But what exactly are black holes? A black hole forms when a massive star reaches the end of its life. As it runs out of nuclear fuel, the star's outer layers are ejected in a brilliant explosion known as a supernova. What remains of the star's core collapses under its own immense gravity, creating a region of space where gravity becomes so intense that not even light can escape. This cosmic marvel defies our understanding of physics and raises profound questions about the nature of the universe. This region is what we call a black hole, a place where space and time are warped beyond recognition. A black hole is not an object we can see directly, but rather it is a region in space defined by the gravitational pull it exerts on everything around it. Even though black holes are invisible, their presence can be detected by the effects they have on nearby objects, such as stars and gas clouds. As matter spirals toward a black hole, it forms an accretion disk, a glowing disk of superheated material that emits intense radiation observable even from the Earth. This energy release is so powerful that it can outshine entire galaxies, serving as a beacon for astronomers searching for these elusive entities. The event horizon is what defines the boundary of a black hole. It is the point of no return, where the gravitational pull becomes so strong that nothing, not even light, can escape. Beyond this boundary lies the singularity, a point where the known laws of physics break down completely. It's a place of infinite density, where the very fabric of space and time collapses into an unfathomable state. Scientists theorize that the singularity may hold answers to some of the most profound mysteries of existence, but it remains inaccessible to observation, hidden behind the event horizon. The concept of black holes first emerged in the 18th century, when John Michell proposed the idea of dark stars, objects so massive that their gravity could prevent even light from escaping. This early speculation laid the groundwork for later developments in the 20th century, when Albert Einstein's general theory of relativity redefined our understanding of gravity and space-time. In 1916, Carl Schwarzschild provided the first mathematical description of a black hole, introducing the concept of the event horizon. For decades, black holes were considered theoretical constructs, but observational breakthroughs in the 1960s changed that perception. The discovery of quasars, luminous and energetic objects powered by supermassive black holes, offered indirect evidence of their existence. This was followed by the identification of Cygnus X1, a binary system where a massive unseen companion, later confirmed as a black hole, emitted intense X-rays as it accreted matter from its visible partner. Stephen Hawking's groundbreaking work in the 1970s brought a quantum perspective to black holes, proposing that they emit radiation, now known as Hawking radiation, and could eventually evaporate over time. These insights expanded our understanding of black holes' thermodynamic and quantum properties. The most dramatic confirmation of black holes came in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's shadow in the galaxy M87. This achievement marked a new era in astrophysics, providing direct visual evidence of these mysterious cosmic phenomena and solidifying their place as essential components of the universe. Black holes are incredibly dangerous because their immense gravitational pull can capture anything that ventures too close, making escape impossible. They can disrupt or destroy entire star systems, distort space and time, and emit deadly radiation during the process of consuming matter, posing a threat to anything in their vicinity. When an object gets too close to a black hole, it enters the event horizon, where the gravitational pull becomes so strong that escape is impossible, even for light. As the object approaches, it experiences spaghettification, extreme stretching due to the black hole's intense tidal forces, pulling more strongly on the side closer to the black hole. The object is ultimately torn apart and consumed, adding to the black hole's mass and energy. Luckily, there are no immediate dangers to Earth from black holes. The closest known black hole, V616 Monoceratus A06200, is about 3,000 light-years away, far too distant to affect us. Additionally, black holes do not roam the galaxy, consuming everything in their path. They only affect objects within their immediate gravitational reach. However, if a black hole were to pass close to our solar system, it could disrupt planetary orbits, strip away the sun's outer layers, or even consume nearby matter. Fortunately, such an event is extremely unlikely within the lifespan of our planet. Perhaps one of the most intriguing aspects of black holes is how they affect time itself. Time near a black hole slows down significantly. This phenomenon, known as time dilation, is a result of the intense gravity warping space-time. If you were to observe an object approaching a black hole, you would see it slow down as it neared the event horizon, seemingly frozen in time. For the object itself, however, time would pass normally. But from a distant observer's point of view, it's as if the object is caught in a timeless freeze frame. Not all black holes are created equal. They come in various sizes and categories. First up, we have the already mentioned stellar mass black holes. These are born from the fiery deaths of massive stars. When a star exhausts its nuclear fuel, it collapses under its own gravity, creating a black hole. These cosmic remnants typically range from 3 to 100 times the mass of our Sun. They're often found in binary systems, feasting on matter from a companion star, or quietly drifting through space. Next, we have the elusive intermediate mass black holes, or IMBHs. Ranging from 100 to 100,000 times the Sun's mass, these are the middle children of the black hole family. Scientists believe they form from mergers of smaller black holes or the collapse of dense star clusters. While rare, they provide a critical bridge to understanding how black holes grow. Next on the list are the true giants, supermassive black holes. These monsters can tip the scales at millions or even billions of solar masses. Found at the hearts of galaxies, like our very own Milky Way's Sagittarius A, they've been growing for billions of years by devouring matter and merging with other black holes. Their gravitational influence is so profound that they shape the very structure of their galaxies. Primordial black holes are a theoretical type thought to have formed just after the Big Bang due to high-density fluctuations in the early universe. Their sizes could range from microscopic to several solar masses. Some scientists even speculate they could account for part of the universe's dark matter, though their existence remains a cosmic mystery. Finally, we have the intriguing concept of miniature or micro black holes. These tiny black holes, possibly smaller than atoms, could form in high-energy cosmic events, or even particle accelerators. According to Stephen Hawking's theory, they emit radiation and eventually evaporate over time. While none have been observed, their discovery would revolutionize our understanding of physics. Black holes are not just destroyers, they also play a vital role in the cosmos and in our study and understanding of the universe. Supermassive black holes influence star formation, galactic structure, and even the distribution of matter in the universe. Without them, the galaxies as we know them might not exist. Some black holes are quiet and invisible, while others are surrounded by swirling disks of gas and dust, which heat up as they spiral toward the event horizon. These glowing accretion disks emit intense radiation that can be observed from Earth, allowing astronomers to study the secrets of these enigmatic objects. Through these observations, scientists gain insights into the dynamic processes that govern the universe. After exploring the origins and types of black holes, as well as the dangers they pose, let's dive into some of the most fascinating areas of research surrounding these enigmatic objects. From gravitational waves to the mind-bending mysteries of the universe's fate, black holes continue to challenge our understanding of the cosmos. One groundbreaking area of study is the detection of gravitational waves, ripples in space-time that were first directly observed in 2015 by the LIGO experiment. These waves, caused by the collision of two black holes, provided us with an entirely new way to study these cosmic giants. The energy released during such mergers not only produces gravitational waves, but can also affect star formation and galactic dynamics. This discovery has opened up an entirely new branch of astronomy, allowing us to hear the universe in a way that was once thought impossible. Black holes may even hold the secrets to the universe's ultimate fate. Some theories propose that the eventual merging of all supermassive black holes could trigger a cataclysmic event, possibly leading to a big rip that could reshape the very fabric of reality. Alternatively, black holes might play a role in the birth of new universes, supporting the idea of a multiverse. In this scenario, the singularity at the heart of a black hole could serve as the birthplace of entirely new realities, offering a radically different view of the cosmos. Then, there's the black hole information paradox, a puzzle that sits at the intersection of quantum mechanics and general relativity. According to quantum theory, information can never be destroyed, yet anything that falls into a black hole appears to vanish forever. This paradox has baffled scientists for decades, and resolving it may unlock profound insights into the nature of space, time, and the very structure of the universe itself. As we deepen our exploration of black holes, we not only uncover their role as cosmic predators, but also their significance as creators and regulators in the vast symphony of the universe. In their infinite darkness, they hold the light of countless mysteries waiting to be unveiled. From their formation in stellar deaths, to their role in shaping galaxies, their connection to dark matter, their ability to stretch time, and their potential connections to the early universe, black holes remain one of the most captivating subjects in modern astrophysics. They remind us of the vast unknowns that lie beyond our current understanding, urging us to continue our quest for knowledge in the depths of space. Building on our journey through black holes, we now turn to another fascinating stellar remnant, the neutron star. These incredibly dense objects are the aftermath of a massive star's death, offering a glimpse into some of the most extreme conditions in the universe. But what exactly is a neutron star, and why does it captivate scientists? A neutron star forms when a massive star runs out of fuel and explodes in a supernova. The core that remains is astonishingly dense, packed with neutrons that resist collapse. Despite having up to twice the mass of our Sun, a neutron star is compressed into a sphere only about 20 kilometers in diameter, roughly the size of a small city. The result is a stellar remnant with gravity so intense that it warps space and time itself. Yet, its dense core is stable, thanks to the quantum pressure of neutrons pushing back against further collapse. What makes neutron stars even more intriguing is their extreme density. Just a teaspoon of neutron star material would weigh about 6 billion tons on Earth. These objects also possess magnetic fields trillions of times stronger than Earth's, creating environments where extreme physical phenomena unfold. The combination of intense gravity, rapid rotation, and powerful magnetic fields leads to some of the most unusual behaviors observed in the universe. Many neutron stars spin at incredibly fast speeds. Some rotate hundreds of times per second. This rapid rotation causes them to emit beams of electromagnetic radiation, which we observe as regular pulses of light, giving rise to the name pulsars. These rhythmic emissions are so reliable that they serve as cosmic clocks, allowing scientists to study everything from the bending of space-time to the behavior of matter under extreme conditions. Pulsars are just one of the remarkable forms that neutron stars take, setting the stage for even more mysterious objects like magnetars, which take these extreme properties to the next level. As we explore neutron stars further, we'll uncover the various ways they manifest in the universe, including the mind-bending phenomena of pulsars, magnetars, and quasars, each revealing a deeper layer of the universe's hidden complexities. The discovery of neutron stars evolved through significant breakthroughs in astrophysics. In the 1930s, Baade and Zwicky proposed that massive stars could collapse into incredibly dense remnants after a supernova. Later, in 1934, Lev Landau suggested these remnants might be made of neutrons, though the idea remained speculative for some time. The real breakthrough came in 1967 when Jocelyn Bell Burnell, working with Anthony Hewish, detected a regular pulse of radio waves from space. Initially thought to be an alien signal, it was soon identified as coming from a rapidly rotating neutron star known as a pulsar. This discovery confirmed the existence of neutron stars and sparked further investigation into their properties. As research progressed, scientists discovered that neutron stars could possess immense magnetic fields and rotate at incredible speeds. This led to the identification of magnetars in the 1980s, neutron stars with even stronger magnetic fields. These objects have since become a crucial focus for understanding extreme physical phenomena in the universe. Today, while we have yet to directly image many neutron stars, astronomers estimate that there could be over 100 million neutron stars in our galaxy alone. To date, only a handful have been imaged, with the most famous being the pulsar in the Crab Nebula, thanks to its observable pulses. The study of these neutron stars, from pulsars to magnetars, continues to unveil the universe's most extreme environments. Neutron stars are dangerous due to their extreme properties, particularly their intense gravity, density, and magnetic fields. One of the most striking dangers is their immense gravity. A neutron star's gravitational pull is so strong that it can warp space and time. If an object were to get too close, the tidal forces would stretch it out in a process called spaghettification, tearing it apart before it could escape. Another threat is the intense radiation emitted by neutron stars, especially if they are actively accreting material. This radiation, including X-rays and gamma rays, could have harmful effects on nearby environments. While this radiation is confined to the region around the star, it poses a risk to anything that ventures too close. Some neutron stars, particularly those with stronger magnetic fields, can create highly energetic bursts of radiation. While these magnetic fields are incredibly powerful, they are contained within the region surrounding the star and do not extend far enough to affect Earth. While these dangers are real, neutron stars are typically located far from Earth, so as far as we know, they pose no threat to us. Neutron stars, despite their dangers, offer some incredible benefits to science and our understanding of the universe. First, they serve as natural laboratories for extreme physics. With their immense gravity, density, and magnetic fields, neutron stars allow scientists to study matter in conditions that simply can't be replicated on Earth. These extreme environments challenge our understanding of everything from quantum mechanics to general relativity, helping us unlock some of the deepest mysteries of the cosmos. Neutron stars also play a key role in the study of gravitational waves. When two neutron stars merge, they release powerful ripples in spacetime that can be detected by observatories like LIGO. This gives scientists a unique way to study the universe and explore phenomena like black holes and the nature of gravity itself. By studying neutron stars, we gain a better understanding of stellar evolution. These objects are the remnants of massive stars that have exploded in supernovae. So by examining them, we learn more about the life cycles of stars and how galaxies and elements are formed. So, while they may be dangerous up close, neutron stars are key to unlocking some of the greatest scientific discoveries of our time. Now that we've explored the fascinating world of black holes and neutron stars, it's time to dive into one of the most intriguing phenomena in the universe: pulsars. Pulsars are a type of neutron star, but with a unique twist. These rapidly rotating, highly magnetized objects emit beams of electromagnetic radiation from their magnetic poles. As the pulsar spins, these beams sweep across space like a cosmic lighthouse, creating regular pulses of light and energy that can be detected from Earth. This rhythmic flashing makes pulsars some of the most reliable cosmic timekeepers we know, and their study has revealed astonishing insights into the behavior of matter under extreme conditions. Let's explore how these extraordinary objects work and why they've become a key focus in astrophysics. The discovery of pulsars in 1967 marked a groundbreaking moment in astrophysics. While scientists had already theorized the existence of neutron stars, it wasn't until Jocelyn Bell Burnell, a young PhD student, and her advisor Anthony Hewish made their historic find that pulsars were confirmed. Bell was working with a radio telescope when she noticed a strange, regular pulse of radio waves coming from space. Initially, they thought it could be a signal from an extraterrestrial civilization, but further analysis revealed that the pulses were coming from a rapidly rotating neutron star, what we now call a pulsar. This discovery completely changed our understanding of neutron stars, proving that they weren't just dense remnants of supernovae, but active, dynamic objects emitting powerful beams of radiation. The pulsar's regular, almost clock-like pulses turned them into an invaluable tool for studying the universe. Following this initial discovery, astronomers found more pulsars, and over time their various properties became clearer. Pulsars are now recognized for their incredible precision, with some capable of keeping time more accurately than the best atomic clocks on Earth. The discovery of millisecond pulsars, those rotating hundreds of times per second, furthered our understanding of these objects, showing that pulsars could be spun up by the accretion of matter from a companion star. The study of pulsars has since revealed a wealth of information about the nature of matter under extreme conditions, the behavior of magnetic fields, and even the structure of space-time itself, making them one of the most exciting areas of research in astrophysics. Pulsars, as a type of neutron stars, are born from the remnants of massive stars that have gone through a supernova explosion. When a massive star reaches the end of its life, it exhausts its nuclear fuel and collapses under its own gravity, triggering a supernova, an incredibly powerful explosion that blasts the outer layers of the star into space. What remains is the core, which collapses further into an incredibly dense object known as a neutron star. Not all neutron stars become pulsars, though. For a neutron star to become a pulsar, it must have a very specific set of characteristics. The star must be rapidly spinning and have a strong magnetic field. When the neutron star forms, its rotation speeds up dramatically due to the conservation of angular momentum. This is similar to how a figure skater spins faster when they pull in their arms. The neutron star's magnetic field, which is already extremely strong, can become highly concentrated at its poles. These strong magnetic fields generate powerful beams of electromagnetic radiation, typically in the form of radio waves, X-rays, or gamma rays. As the neutron star spins, these beams sweep across space, and if Earth lies in the path of the beams, we detect regular pulses of radiation, hence the name pulsar. The rate of rotation and the strength of the magnetic field determine the frequency and regularity of the pulses, which can range from once every few seconds to several hundred times per second, in the case of millisecond pulsars. Some pulsars also undergo glitches, sudden, unexplained changes in their rotation rate, which adds another layer of mystery to their behavior. Pulsars come in a few different types, each with unique traits and behaviors, but all of them share one fascinating characteristic. They emit regular pulses of radiation, like cosmic lighthouses. Let's dive into the different kinds of pulsars we've discovered. First up, radio pulsars are the most common and were the first type discovered. These pulsars emit regular pulses of radio waves, and their spin rates typically range from once every few seconds to about 1 per minute. Their regularity makes them some of the universe's most reliable cosmic clocks. Then, there are the millisecond pulsars, a subclass of radio pulsars that rotate incredibly fast, sometimes up to several hundred times per second. This rapid spinning happens when the pulsar is in a binary system, pulling material from a companion star, causing it to speed up over time. They're incredibly precise, and some are even used for testing theories like general relativity. X-ray pulsars are a bit different. These pulsars emit periodic bursts of X-rays, usually in a binary system. The neutron star pulls matter from its companion, forming an accretion disk, which heats up and emits X-rays as it spirals into the pulsar. This process results in the characteristic pulsing of X-rays, which we can observe. For even more energetic pulsars, there are gamma-ray pulsars. As the name suggests, they emit high-energy gamma rays, the most powerful form of radiation. These pulsars are similar to radio pulsars, but their emissions are much higher in energy. They can't be detected from Earth with regular telescopes because gamma rays are blocked by our atmosphere, so special space-based telescopes are needed. Another fascinating category is anomalous X-ray pulsars, AXPs. These are X-ray pulsars with unusual properties. They emit persistent X-rays, but scientists believe their energy comes from incredibly strong magnetic fields, possibly even stronger than typical neutron stars. AXPs are thought to be part of a group of pulsars known as Magnetars, which have magnetic fields so powerful they can even affect the surrounding space. Then we have soft gamma-ray repeaters, SGRs, which are pulsars that emit intense bursts of gamma rays. SGRs are similar to AXPs in that they are thought to be magnetars, and their outbursts are linked to the extreme magnetic fields at the heart of the pulsar. Binary pulsars are another intriguing type. These are pulsars that exist in binary systems, where they orbit around a companion star. Sometimes the pulsar's gravity can strip material from the companion, creating a strong interaction between the two. In some cases, these systems help astronomers test theories about gravitational waves and the nature of space-time, as the pulsar's timing can be incredibly precise. Lastly, Black Widow and Redback pulsars are unique in that they are part of binary systems, where the pulsar is so powerful it actually feeds on its companion. The term Black Widow comes from how the pulsar essentially consumes its partner, while redback pulsars are similar, though with less extreme behavior. Each type of pulsar offers a different glimpse into the nature of the universe, from the extreme gravitational and magnetic forces at play to the mysteries of matter under the most extreme conditions. Pulsars continue to be one of the most captivating subjects in astrophysics, unlocking secrets about the universe's most extreme environments. Pulsars aren't just fascinating objects, they're some of the most precise natural clocks in the universe. Their regular pulses are so incredibly accurate that scientists can measure time with nanosecond precision. This makes them invaluable tools for testing theories of general relativity and even creating cosmic-scale GPS systems. Millisecond pulsars, in particular, allow astronomers to detect tiny changes in their pulses, which can reveal things like gravitational waves, ripples in spacetime caused by massive cosmic events. Speaking of extreme speeds, did you know that pulsars can spin incredibly fast? The fastest known pulsar, PSR J17482446AD, spins a mind-blowing 716 times per second. That's faster than a blender's blade. These rapid rotations push the limits of physics and help us understand the boundaries of how fast a star can spin before it shatters. But pulsars do more than just spin. They also play a key role in detecting gravitational waves. By studying the regularity of their pulses, astronomers can detect the tiny distortions in space-time caused by waves from massive cosmic collisions, like black hole mergers. This technique allows us to hear the universe in a way that was once thought impossible. Inside a pulsar, the matter is unlike anything we can replicate on Earth. The neutron star's density is so extreme that a single teaspoon of pulsar material would weigh 1 billion tons. Studying these objects gives us a glimpse into the properties of matter, under conditions we can't reproduce in labs, helping scientists probe the most extreme environments in the universe. Pulsars also produce energetic winds of particles that interact with surrounding gas to create pulsar wind nebulae, glowing clouds of particles that stretch across vast distances. These nebulae, often found in the remnants of supernovae, are visual proof of the power and energy pulsars can unleash. The signals from pulsars also offer us a way to study the interstellar medium, the gas and dust between stars. As pulsar signals travel through this space, they change, giving scientists a unique radar to map the structure of the universe in between stars. Interestingly, pulsars were once thought to be possible signals from extraterrestrial civilizations, due to their precise repeating nature, though this theory was quickly ruled out. It shows just how remarkable and mysterious pulsars are in the search for life beyond Earth. And let's not forget the binary pulsars, two neutron stars orbiting each other. These systems allow us to test Einstein's theory of general relativity in extreme conditions. In fact, the famous PSR B1913+16 binary pulsar system provided the first indirect evidence of gravitational waves, confirming a key prediction of general relativity. So, pulsars are much more than just fast spinning stars. They're timekeepers, cosmic laboratories, and even players in the search for gravitational waves. They help us understand everything from the structure of matter to the fundamental laws of physics. Now that we've explored the mysterious world of black holes, neutron stars, and pulsars, let's dive into one of the most extreme and fascinating types of neutron stars, magnetars. These rare and powerful objects are similar to pulsars in that they're incredibly dense, but they differ in one key aspect: their magnetic fields. Magnetars are thought to have the strongest magnetic fields in the entire universe, capable of generating intense radiation and even distorting space itself. These magnetic forces are so extreme that they can rip apart atoms, and the energy released can produce some of the most powerful bursts of radiation known to science. Let's explore what makes magnetars so unique and what they reveal about the nature of the universe. Magnetars are formed in much the same way as other neutron stars, through the collapse of a massive star's core after a supernova explosion. However, what sets magnetars apart is the extreme magnetic field they inherit. This strong magnetic field likely results from the rapid rotation and intense pressure within the neutron star during its formation. Some scientists believe that magnetars are the product of a particularly violent supernova, where the progenitor star's core experiences extreme compression, amplifying its magnetic field to catastrophic levels. The key factor that determines whether a neutron star becomes a pulsar or a magnetar lies in the strength and configuration of its magnetic field and its rotation. Neutron stars that have relatively weaker magnetic fields and a more typical rotational speed tend to become pulsars. These pulsars emit beams of radiation due to the alignment of their magnetic poles and rotation, creating the observable pulses we detect from Earth. On the other hand, magnetars have incredibly strong magnetic fields, around 1,000 times stronger than typical neutron stars. These fields are so powerful that they can influence the star's structure and behavior, leading to violent bursts of gamma rays and X-rays. Magnetars don't necessarily pulse in the same way that regular pulsars do, but they do produce massive energy flares caused by their magnetic field instability. In short, whether a neutron star becomes a pulsar or a magnetar depends on the strength of its magnetic field and its rotational characteristics, both of which stem from the conditions present during its formation. Magnetars were first predicted in the 1970s, but their discovery came much later. The theoretical groundwork for magnetars was laid by astrophysicists who were trying to understand the behavior of neutron stars. While studying neutron stars, researchers found that their magnetic fields could be far stronger than previously imagined. This led to the hypothesis that some neutron stars could possess magnetic fields so intense they would fundamentally alter the way the star behaves. The term magnetar was coined in 1992 by astronomers Robert Duncan and Christopher Thompson, who proposed that certain neutron stars could have magnetic fields up to 1,000 times stronger than the typical neutron star. These fields would be strong enough to cause catastrophic phenomena like giant bursts of X-rays and gamma rays, far more powerful than what was observed from regular pulsars. Magnetars were finally discovered in 1998, when the first candidate magnetar, SGR 1900+14, was identified. This star emitted a burst of gamma rays, a signal that couldn't be explained by conventional neutron stars or pulsars. Following this discovery, several more magnetars were found, each displaying similar bursts of high-energy radiation. Their extreme magnetic fields were confirmed as the source of these violent outbursts. Since their discovery, magnetars have been a subject of intense study, not only for their powerful magnetic fields, but also for the insights they offer into the behavior of matter under extreme conditions. These stars are rare. There are thought to be only about 30 known magnetars in our galaxy, and they remain some of the most extreme and fascinating objects in the universe. Magnetars are dangerous primarily because of their incredibly powerful magnetic fields, which can reach up to 1,000 times stronger than a typical neutron star. These fields can be so intense that they can distort the structure of atoms, ripping apart the very matter around them. A magnetar's magnetic field is strong enough to potentially induce electric currents in nearby objects, and even cause the destruction of electronic equipment from light years away. What truly makes magnetars dangerous, however, are their outbursts of energy. These bursts of gamma rays and X-rays are extremely high energy and can last from milliseconds to seconds. The energy released during these outbursts is on such a massive scale that if one occurred close enough to Earth, it could damage the planet's atmosphere, potentially disrupting the ozone layer and exposing life to harmful radiation. Fortunately, magnetars are incredibly rare, and the closest known magnetar is about 13,000 light-years away, far enough that we don't have to worry about these outbursts affecting us directly. While the danger to Earth from a magnetar is minimal due to their vast distance, these extreme objects do pose a significant threat to any star systems or planets that come too close. The radiation and magnetic fields of a magnetar can affect the environment of nearby planets, and in some cases may even cause the destruction of planetary atmospheres or interfere with life-supporting conditions. But overall, these events happen far away, and for us on Earth, magnetars remain a fascinating yet distant cosmic mystery. Magnetar bursts are one of the most extreme and violent phenomena in the universe. These bursts, primarily in the form of gamma rays and X-rays, are produced by the unstable magnetic fields of magnetars. The intense magnetic field of a magnetar is not static. It is constantly shifting, twisting, and sometimes breaking apart. When these magnetic fields rearrange, they release enormous amounts of energy, leading to powerful bursts of radiation. There are two main types of bursts associated with magnetars: soft gamma repeaters, or shortly SGRS, are relatively short-lived bursts of gamma radiation that can last from a few milliseconds to a few seconds. They can release more energy in a fraction of a second than the Sun does over the course of its entire 10 billion year life. These bursts are typically seen in clusters, with several smaller bursts following the main outburst. Anomalous X-ray pulsars, AXPs. These are a different type of magnetar that also produce powerful X-ray bursts. AXPs have been observed to emit more sustained and intense bursts than typical neutron stars, and their bursts are often highly variable, with unpredictable fluctuations in their radiation. These bursts are triggered by starquakes, massive sudden releases of energy caused by shifts or cracking in the magnetar's crust due to the immense magnetic forces at work. When these shifts occur, they can cause a surge of energy, releasing it in the form of highly energetic bursts of X-rays and gamma rays that can be detected across vast distances. Magnetar bursts are so powerful that they can disrupt nearby space and time. For instance, they have the potential to influence the behavior of atoms and molecules, and their energy can even ionize surrounding matter. Although these bursts are incredibly bright, they are very short-lived, typically only lasting a fraction of a second to a few seconds. However, their impact is immense. For example, the burst from the Magnetar SGR 180620 in 2004 was one of the most powerful gamma-ray bursts ever observed and released as much energy in a few milliseconds as the Sun does in 150,000 years. While the energy released by magnetar bursts is extreme, they're usually not a direct threat to Earth due to the vast distances between us and these objects. However, if a magnetar were located closer to our planet, its bursts could potentially pose a danger by disrupting Earth's atmosphere and damaging satellites or electronics. But fortunately, the nearest magnetars are located thousands of light-years away, making them a fascinating but distant cosmic phenomenon. We've journeyed through the cosmos, exploring the terrifying wonders of black holes, neutron stars, pulsars, and magnetars. These celestial phenomena are powerful and awe-inspiring, but they pale in comparison to the cosmic beacons that light up the universe itself. Quasars. Quasars are the ultimate cosmic enigmas, outshining entire galaxies while sitting at their very hearts. Powered by supermassive black holes, these extraordinary objects are like lighthouses of the early universe, revealing the distant past and the violent processes that shape galaxies as we know them. But what exactly are quasars? How do they produce such mind-bending energy? And what secrets do they hold about the formation of our universe? As we approach the final leg of this cosmic adventure, prepare to dive into the dazzling and dangerous world of quasars, where the forces of creation and destruction collide in a spectacular display of raw power. Quasars, or quasi-stellar objects, are among the brightest and most energetic phenomena in the universe. At their core lies a supermassive black hole, millions to billions of times the mass of our Sun, surrounded by a swirling accretion disk of gas, dust, and other matter. As this material spirals toward the black hole, it heats up to millions of degrees, releasing an incredible amount of energy in the form of light, radio waves, and even X-rays. What makes quasars so extraordinary is their sheer luminosity. A single quasar can outshine the combined light of all the stars in its host galaxy, making it visible across billions of light years. The brightest quasars are some of the most distant objects ever observed, acting as time machines that allow us to peer back into the early universe. Quasars are powered by the insatiable hunger of their central black holes. As matter falls into the accretion disk, it not only produces light, but also generates powerful jets of charged particles that shoot out from the poles of the black hole at nearly the speed of light. These jets can stretch for thousands of light years, influencing the formation of stars and the structure of galaxies around them. Despite their incredible energy, quasars are not permanent fixtures. They represent an active phase in the life of a galaxy, typically occurring when a supermassive black hole consumes a large amount of matter. Once the fuel supply is exhausted, the quasar dims, leaving behind a quieter, more stable galaxy. In essence, quasars are cosmic powerhouses, reminders of the universe's chaotic, violent youth and the astonishing capabilities of supermassive black holes. They are not just fascinating, they are also essential for understanding the origins and evolution of galaxies, including our own. The story of quasars begins in the late 1950s and early 1960s, when astronomers were mapping the sky using radio telescopes. They detected mysterious radio sources that didn't align with any known objects. One of these sources, later identified as 3C273, appeared particularly perplexing. Optical telescopes revealed it was associated with a star-like object, but its light spectrum was unlike anything seen before. In 1963, Dutch-American astronomer Martin Schmidt made a groundbreaking discovery while studying 3C273. By analyzing its redshift, the way light stretches as it travels through the expanding universe, he realized the object was much farther away than any known star. For it to appear so bright from such a distance, 3C273 had to be emitting unimaginable amounts of energy. This marked the discovery of quasars, or quasi-stellar radio sources, objects that looked like stars but were far more powerful. Further research revealed that quasars were powered by supermassive black holes at the centers of galaxies. As matter spirals into these black holes, it forms an accretion disk, releasing enormous energy that outshines entire galaxies. The term quasar eventually expanded to include objects that emit primarily visible light, not just radio waves. Quasars were initially mysterious anomalies, but they quickly became key to understanding the universe. They offered insights into galaxy evolution, black hole growth, and the conditions of the early cosmos. Today, they are not just some of the brightest objects in the universe, they are beacons illuminating its deepest mysteries. We have since discovered many more quasars, a few of which stand out for their sheer power, mystery, or ability to reshape what we thought was possible. Let's explore three of the most captivating quasars discovered so far. TON 618 isn't just a quasar, it's a cosmic giant. Located about 10.4 billion light-years away, this quasar is home to one of the most massive black holes ever discovered. With an estimated mass of 66 billion times that of our Sun, TON 618's black hole dwarfs anything we've ever encountered in the universe. To put that in perspective, its event horizon would be large enough to engulf our entire solar system many times over. The light from this quasar is so intense that it outshines entire galaxies, and it's visible across billions of light years. TON 618 is a humbling reminder of the universe's capacity for extremes, showcasing a black hole that defies the limits of growth and challenges our understanding of cosmic evolution. Ulysses J134202928 is the most distant quasar ever discovered, located an incredible 13.1 billion light-years away. Its light began its journey when the universe was just 690 million years old, making this quasar a rare time capsule from the cosmic dawn. At its core lies a supermassive black hole with a mass 800 million times that of the Sun, an almost impossible feat for such an early period in the universe's history. How could such a massive black hole form so soon after the Big Bang? Scientists are still searching for answers, and Ulysses J134202928 continues to reshape our theories about galaxy and black hole formation during the early universe. APM 08279-5255 is a quasar with an extraordinary claim to fame. It hosts one of the largest reservoirs of water ever discovered in the universe. Located 12 billion light-years away, this quasar surrounds itself with enough water vapor to fill Earth's oceans 140 trillion times over. But that's not all. This water-rich environment exists in extreme conditions near a supermassive black hole, where temperatures reach hundreds of degrees Kelvin. The quasar's light is magnified by a natural gravitational lens, allowing astronomers to study its structure and revealing its unimaginable scale. APM 08279-5255 isn't just a quasar, it's a cosmic oasis, showing us that even the most hostile environments can harbour the building blocks of life. Each of these quasars offers a unique glimpse into the extremes of the universe, from the monstrous power of black holes to the mysteries of the early cosmos, and even hints of water on unimaginable scales. They are not just objects to observe, they are profound questions waiting to be answered. Quasars are not only dangerous because of their gravitational pull, they are also terrifying due to the jets of high-energy particles they emit. These jets can extend thousands of light-years into space, emitting radiation across the electromagnetic spectrum. They are created when material in the accretion disk gets funneled along the black hole's magnetic field lines, forming two powerful beams that shoot out from the poles of the black hole at nearly the speed of light. The energy emitted in these jets can be staggering. Quasar jets are capable of accelerating particles to near-light speeds, creating shock waves that can disrupt the interstellar medium and even the formation of stars in nearby galaxies. These jets can impact large regions of space, heating gas to millions of degrees and stripping away the material that would otherwise go on to form new stars and planets. In the most extreme cases, the jets can disrupt the formation of galaxies altogether, altering the evolution of the universe on a cosmic scale. The destructive power of these jets is not only theoretical. Observations have shown that quasar jets can have catastrophic effects on their host galaxies. In one example, the already mentioned Quasar 3C 273, a relatively nearby quasar in the constellation Virgo, was observed emitting powerful jets that extended across vast distances. These jets are capable of stripping gas from neighbouring galaxies, preventing star formation and causing significant disruption to the surrounding space. In some cases, the jets of quasars can interact with their environment in ways that cause violent shockwaves. These shockwaves can ignite new star formation in some regions, but in others, they can halt the formation of stars by heating up the surrounding gas to extreme temperatures, preventing it from condensing into new stars. This dual nature of quasar jets, both destructive and constructive, makes them one of the most fascinating yet terrifying phenomena in the universe. While most quasars are located billions of light-years away from Earth, the intense radiation and energetic particles they emit have the potential to affect us, at least in theory. If a quasar were to be located much closer to our galaxy, its radiation could have catastrophic effects on our planet. The energy produced by a nearby quasar could strip away the Earth's atmosphere, expose the planet to harmful radiation, and even cause mass extinctions. Though the likelihood of such an event occurring is remote, the idea of a nearby quasar emitting a blast of high-energy radiation directed at Earth is a reminder of the inherent dangers of the universe. While the majority of quasars are located in distant galaxies, the sheer scale and power of these objects serve as a humbling reminder of how small and fragile our existence truly is in the context of the cosmos. Quasars are among the most terrifying and awe-inspiring objects in the universe. They represent the extremes of cosmic power, with their supermassive black holes capable of destroying entire galaxies and emitting radiation that can disrupt the very fabric of space-time. While they are often located far away, the immense energy emitted by quasars serves as a reminder of the incredible forces that shape the universe. From their powerful gravitational pull to their catastrophic jets, quasars are objects of immense fascination and fear. Their role in the evolution of galaxies and their potential dangers make them a topic of great importance in astrophysics. While quasars may seem like distant, abstract phenomena, their presence in the cosmos reminds us of the vast and often terrifying forces that govern the universe. Quasars are not just distant beacons of light, they are symbols of the power and danger that lie beyond our understanding, waiting to be uncovered. From the all-consuming void of black holes to the cosmic beacons of quasars, we've seen just how ruthless and deadly the universe can be. Each of these objects serves as a stark reminder of how small we are in the grand scale of space, and how easily everything we know could be wiped out by forces beyond our control. But even in the face of such unimaginable terror, the study of these cosmic giants pushes our understanding of the universe and the very fabric of reality itself. So, next time you look up at the night sky, remember, out there, something truly terrifying could be watching, and it's only a matter of time before we discover something even more deadly than we've ever imagined. Thanks for watching, and don't forget to subscribe for more journeys into the cosmos' darkest corners.